What is the sum of n natural numbers? So your instant answer might be n times n plus 1 divided by 2. If this is your answer for this question, congratulations, you are correct. And you feel like easy QC, lemons QC. So let's continue further. How do we prove this? So let's denote the sum by yes, 1 plus 2 plus 3 plus on and on and on up to n as yes. So if we reverse the sum as n plus n by n minus 1 plus n minus 2 plus on and on and on up to 1, it will be also denoted as yes, because rearranging doesn't change the value of sum. So it will be also denoted by yes. So if we add the add those expressions, this expression plus this expression, we get 2s. 2s equal to n plus 1 times n. So if we divide out this expression by 2, we get the sum as n times n plus 1 divided by 2. Intuitively, this suggests that there are n pairs of n plus 1. So if we want the sum, we have to divide this expression by 2. So the sum will be n times n plus 1 divided by 2. So we are going to find what is the sum of squares of n natural numbers. The answer will be n times n plus 1 times 2n plus 1 divided by 6. So let's continue further. What is the sum of cube of n natural numbers? Some curious followers among you will answer it as n times n plus 1 divided by 2 the whole square. So if this is your answer, congratulations, you are correct. Let's go one step further. What is the sum of fourth powers of n natural numbers? Even curious followers among you will answer for this question. The answer will be some complicated expression that looks something like this. So if we go one step further, what is the sum of fifth powers of n natural numbers? So how do we proceed? What is the sum of fifth powers of n natural numbers? I don't know the answer. How do we proceed to get the sum? So let's proceed as follows. Before that, we are going to see what are Bernoulli numbers. Bernoulli numbers, as defined by Wolfram alpha, it is the coefficient of the series expansion of x upon e power x minus 1. The Wolfram alpha suggests that it is the coefficient of the expression x upon e power x minus 1. Series expansion means the Taylor series expansion of the function x upon e power x minus 1. So the first few Bernoulli numbers can be calculated as b naught equal to 1. The first Bernoulli number is 1, and the second Bernoulli number is denoted by b sub 1 is minus 1 by 2, and the second Bernoulli number is denoted by b sub 2 and it is 1 by 6, and third Bernoulli number which is denoted by b3 which is equal to 0, and we go on forever. So if we carefully look at this expression, you may notice that the odd Bernoulli numbers are 0 except the first Bernoulli number which is minus 1 by 2. So the Wolfram alpha suggests that these are the Bernoulli numbers. If this is hard to follow, I encourage you to follow this expression. So it defines the Bernoulli number in a recursive fashion. Recursive fashion in the sense that if we want to calculate the Bernoulli number, let's say the second Bernoulli number, we have to know the first and the 0th Bernoulli number. If we want the third Bernoulli number, we have to know what is the second, first and the 0th Bernoulli number, right? It is the recursion, right? So we are calculating in a recursive fashion by using this formula, right? So what is the relation between Bernoulli numbers and the sum of squares of kth power of n natural numbers? So let's see. So the kth power of the sum of kth power of n natural numbers is defined in terms of Bernoulli numbers as 1 by k plus 1 summation of p runs from 0 to k minus 1 whole power p k plus 1 choose p times b sub p times n power k plus 1 minus p. It is defined as follows. So initially I asked what is the fifth power of sum of fifth powers of n natural number. So it is calculated with the above formula as follows, and the final expression is n power 6 divided by 6 plus n power 5 divided by 2 plus 5 divided by 12 times n power 4 minus n square divided by 12. It is the sum of fifth powers of n natural numbers. So we can calculate the sum of any power of n natural number by using this formula in terms of Bernoulli numbers. So let's wind up this video and let's see in the next video. Thank you.